Space stretches endlessly in every direction, silent yet full of motion. Stars shimmer like distant fires scattered across a dark ocean, and among them drifts our own small neighborhood, the solar system. Each planet circles the sun at its own pace, from the fast sweep of Mercury to the slow, cold orbit of Neptune. But how far are they? And how long would it take for us to reach each one? Today, we'll travel step by step across that cosmic distance, from the warmth of the inner planets to the frozen edges of the outer worlds. If you enjoy journeys like this through space and time, take a moment to like and subscribe. It helps keep our adventure going. Now, let's set course for the first stop on our solar voyage. In the quiet after launch, Earth begins to fade beneath us, not as a place, but as a memory slowly dissolving. The roar of engines softens into silence, replaced by the deep, low hum of space. Time seems to stretch, as if the seconds themselves have become heavier. Our journey begins not with speed, but with a change of being. We are no longer bound to the surface of a planet. We are part of something larger, floating in the black expanse between worlds. The metal frame around us trembles, every bolt and panel alive with motion. Millions of pounds of thrust lift us away from everything familiar. In that rising force, we stop being citizens of Earth and become travelers of the void. As gravity weakens its hold, the details of our world blur into one simple, beautiful sight. The oceans, the mountains, and the long ribbons of clouds fold together into a single sphere of color and light. From here, we see Earth whole for the first time. The air fades thin, the sound of wind disappears, and the sky, once blue, becomes deep, velvet black. Crossing the Kármán line, the invisible border between air and space feels like stepping through a curtain. The pressure vanishes. The sun's light is no longer scattered. It burns sharp and clean. There is no dawn, no dusk, only the slow turning of Earth below. Cities blink like faint sparks. Storms crawl across continents in patient spirals. Time, once quick and full of noise, now drifts softly, as if space itself has slowed its heartbeat. Here, motion is not measured by footsteps or wheels, but by orbits and invisible pulls. Every movement is a balance between gravity and momentum. Space travel is not only about distance, it is about learning to let go of the old rules. Up and down lose their meaning. Time itself bends and stretches. What was once steady and familiar becomes flexible, shaped by speed and gravity. The higher we climb, the more the mind expands to hold this new understanding. Space is not empty. It is filled with quiet power. Gravity draws, light curves, even time flows differently, as if the universe moves to its own hidden rhythm. Completing the first orbit, we look down and see Earth glowing softly, fragile yet steady. The lands and oceans that once seemed infinite now fit within a single glance. Borders vanish, nations fade. There is only one living world, spinning in a sea of darkness. This view humbles us. For the first time, we see the planet as it truly is, a single home shared by every life that has ever lived. Humanity has always reached for the stars. Only now do we finally remember how. As our spacecraft aligns for the next maneuver, preparing to leave Earth's embrace, we feel the last pull of home. The tug is both physical and emotional. Each passing second carries us farther from everything we know. Yet there is peace here, a calm born from purpose and curiosity. Beyond Earth stretches a path shaped over billions of years by the movement of planets. We are not forging something new. We are following trails already written in gravity's language. The engines ignite once more. Our orbit becomes escape. We are leaving Earth. From now on, our time will be marked not by days, but by distances. Our lives measured not in hours, but in trajectories. The faint glow of Earth's atmosphere fades behind us, blending into the eternal dark. Still, we do not lose our home. We carry it with us, in memory, in purpose, in hope. Each mile is not just a step away, but a step toward understanding who we are and how we belong to the universe. Beyond the atmosphere, the nature of motion changes. There is no air to slow us, no ground to hold us. Travel here is measured not in miles per hour, but in velocity and gravitational dance. There are no roads or trails between the planets, only invisible paths drawn by forces older than life itself: gravity, momentum, and geometry. These unseen currents shape every journey. Spacecraft must use them carefully, letting gravity bend their paths and build their speed. The art of space travel is not about power, but balance. We do not fight gravity. We use it, like a sailboat catching the wind. A spacecraft lets the pull of planets guide its course. These routes, called transfer orbits, are gentle arcs that link worlds together. They are chosen not for simplicity, but for efficiency. No ship can simply aim straight across the void. It must fall toward its target, moving along the curved fabric of space shaped by planetary mass. Earth's gravity holds us until we reach escape velocity about 7 miles per second. Once past that speed, we are free from its grip, drifting along the solar wind. In this vacuum, motion lasts forever. With no air to resist, every small push continues endlessly until something else changes it. One brief burn of the engines can carry us for months, even years. The challenge now is trade fuel for time. Move fast and burn more energy, or save fuel and accept a slower, longer journey. The planets ahead act like ports along a vast cosmic sea. Their massive gravity can bend our path and speed us onward without a drop of fuel. This is called a gravity assist, and it is one of the most elegant tricks in spaceflight. As we approach a planet, we fall toward it, gaining speed. When we swing past, we steal a little of its motion, turning that energy into our own. The planet slows by an immeasurable fraction, but in return, we gain the boost we need. Even across light years, the rule holds true: nothing moves without cost. These opportunities do not appear at random. They depend on timing, on the perfect alignment of worlds. Planets must line up just right for their gravity to form a smooth bridge across space. Miss that moment, and the door closes. The journey takes longer. The path becomes less efficient. Mission planners sometimes wait decades for the perfect alignment. When Earth, Mars, Jupiter, and Saturn arrange themselves in a rare geometry that opens a clean route through the solar system. As we travel these invisible lanes, it becomes clear that space is not an empty nothingness. It is alive with connection, a vast web of forces linking every object, every motion. Each world pulls on another. Each orbit shapes the next. The universe is not a flat stage, but a moving fabric, always shifting, always in conversation with itself. To travel through space is not to conquer it, but to join its rhythm. We move forward not by resisting, but by listening to gravity, to light, to the quiet architecture that holds everything together. And so we continue, guided not by maps, but by the patient hands of the universe itself. Mercury waits close to the sun, a small world in a deep glare. Reaching it is not a race to go faster. It is a lesson in slowing down. From Earth's path around the sun, Our first instinct is to add speed and charge inward. The inner solar system teaches the opposite. To arrive at Mercury and stay there, a spacecraft must shed energy step by step. Earth moves around the Sun at about 30 kilometers per second. Mercury moves faster, near 47 kilometers per second. As a craft drops sunward, its speed around the Sun rises naturally. That sounds helpful, yet it is not. The goal is not only to touch Mercury, but to match its motion closely enough to be captured. If we arrive too fast, we fly past and back out into space. The challenge is not the distance. The challenge is arriving slow enough to settle into orbit. This is why missions to Mercury use a chain of flybys and gravity assists. Each pass near a planet trims speed by a small but precious amount. The fastest way to reach Mercury for a simple flyby is a direct transfer, which can take roughly 3 to 5 months. Mariner 10 showed this in the 1,970 seconds, reaching Mercury about 4 months after launch. But a quick pass is not the same as staying. To orbit Mercury, patience becomes the main tool. NASA's Messenger, launched in 2004, followed a careful route. It flew by Earth once, Venus twice, and Mercury 3 times. With every swing, it adjusted speed and path. Only in 2011 did it finally ease into Mercury orbit. That was about 6.5 years after leaving Earth. Europe and Japan designed Bepi Colombo with the same logic. 1 Earth flyby, 2 at Venus, then a series at Mercury, spending years trimming speed in the deep sunlight near the Sun before orbital capture. Inward is not easier. Inward is harder. Success comes from small changes made with care. Between these encounters, the spacecraft coasts in bright silence. The Sun grows larger and more intense. Thermal shields become essential. Sunlight near Mercury can be up to 10 times stronger than at Earth. Guidance and control must act with precision. A short engine burn or a tiny change in pointing, made at the wrong time, can shift the final path by thousands of kilometers. The work looks gentle from a distance. It is anything but. Then Mercury fills the window. The world is charcoal gray, heavily cratered, and ancient. It sits in a harsh glare that sharpens every edge. With almost no atmosphere, only a thin exosphere, made of atoms knocked off the surface by sunlight and micrometeorites. There is no wind and no weather. Shadows are clean and hard. The sky is always black. Temperatures swing to extremes. Near local noon, the surface can reach about 430 degrees Celsius, hot enough to glow in infrared. At night, it can drop below 170 degrees Celsius. A year on Mercury lasts about 88 Earth days. But a solar day, from one noon to the next, takes about 176 Earth days, because Mercury rotates 3 times for every 2 orbits. Near the line between day and night, called the terminator, the Sun can appear to pause or even drift backward near perihelion. This effect comes from the special match between Mercury's spin and orbit. Scientifically, Mercury is full of surprises. It has an oversized iron core for its size. It has a global magnetic field, unusual for such a small planet. Its surface shows wide volcanic plains and long curved cliffs called lobate scarps. Those cliffs formed as the hot interior cooled and the whole planet shrank a little, crumpling the crust. Each orbit with a mapping camera adds a new layer to the record of how rocky planets form and age under heat and impact. So how long does it take to reach Mercury? A flyby can be done in months. To stay, the mission can take years. Those years are not wasted time. They are the price of matching paths, shaving speed, and arriving in a way that allows long study. The reward is a stable view of the Sun's nearest neighbor, where space heat, and time reduced to basic forms that test our understanding of worlds. The path then turns toward Venus, a bright point that often glows at dawn or dusk. It looks calm from Earth, smooth and bright, because its clouds reflect much of the sunlight. Getting there is faster than a Mercury orbit, but the world itself is far more hostile. Traveling inward to Venus also means reducing orbital speed around the Sunday. It is not enough to point and go. A launch must wait for the right alignment, a window that comes roughly every 19 months. When timing is right, a Hohmann transfer, a simple and efficient arc between two circular orbits, can reach Venus in about 120 to 150 days. That is 4 to 5 months of quiet flight, with the sun growing larger and the light growing stronger. As the spacecraft falls inward, the sun's pull adds speed. Temperatures inside the craft must be controlled. Radiation levels rise. The target grows from a bright star to a pale disk, and then to a full world wrapped in clouds. Venus shines so well because those clouds throw sunlight back into space. The planet is not a mirror, but it has a high reflectivity called albedo. That is why Venus looks like a steady lantern in the sky. Venus rotates very slowly and in the opposite direction from most planets. One rotation takes about 243 Earth days. A Venusian day is longer than its year. If you could stand on the surface, the sun would appear to rise in the west and set in the east, drifting across the sky so slowly that sunrise and sunset would stretch over weeks. Time there feels stretched and strange, not because time itself changes, but because the planet turns so slowly under a fixed glare. Beneath the clouds, the surface is extreme. The air is made mostly of carbon dioxide. The greenhouse effect is overwhelming. Heat is trapped and builds until the ground reaches about 470 degrees Celsius. The pressure at the surface is more than 90 times that of Earth. It is like standing nearly a kilometer under the ocean. The clouds hold sulfuric acid droplets. They hide the surface from view in visible light and reflect much of the sunlight before it reaches the ground. This is why the world glows from afar and burns up close. For a long time, some imagined Venus as a wet jungle world under a heavy cloud cover. Radar maps and lander data ended that idea. Spacecraft that touched down survived only minutes, crushed and overheated. Metal softens in open air. Electronics fail. The horizon would be a hazy orange line. Volcanic plains would stretch away with low, broad shapes. No blue sky, no stars, just heat and dense cloud above. Yet the upper atmosphere is different. At around 50 kilometers above the surface, the temperature and pressure become closer to those on Earth. This layer has drawn interest for future study. Balloons or airships could float there for long periods, measuring chemistry, clouds, winds, and light, while staying far above the crushing conditions below. The idea is simple. Learn from a safer vantage point while building the tools to look deeper. Venus's winds in the upper atmosphere race around the globe in about 4 Earth days. This fast flow is called superrotation. It is driven by heat and by the way sunlight is absorbed and moved across the planet. Lightning may flash within the clouds. Droplets of acid form and then evaporate before they can reach the ground. Even the term rain loses its normal meaning here. What starts to fall does not arrive. There is evidence that Venus once had far more water. Some scientists think shallow oceans may have pooled on its early surface. Volcanoes would have released large amounts of carbon dioxide. Without a strong global magnetic field to help protect the upper atmosphere, solar radiation can split water molecules. Hydrogen, being very light, escapes to space. Oxygen reacts with rocks. Over long times, the water is lost, the greenhouse effect grows, and the surface becomes a dry, hot desert of rock. This change did not happen in a single event. It took millions of years, driven by steady processes that add up. Venus also appears to be geologically active. The planet holds more known volcanoes than any other world. Many are old, but some signs suggest activity continues. Heat patterns, gas changes, and surface features that look fresh. The crust may be resurfaced from time to time by large eruptions or broad flows. Even without plate tectonics like Earth's, the interior seems to push and shape the outer layers. To reach Venus, the travel time can be just months. The value of the trip is larger than the schedule. Venus tells a story about climate, balance, and change. Earth and Venus formed side by side from the same cloud of dust and gas around the young Sunday. Early on, both may have had clouds, rain, and seas. Earth cooled enough to hold on to liquid water and to form a stable cycle of air, ocean, and rock. Venus went another way. The greenhouse effect grew too strong. Heat rose. Water was lost. The surface changed into what we see today. Studying Venus is a way to check our models for how atmospheres evolve. It tests the limits of habitability. It shows how a planet can cross a line and enter a different state that is hard to reverse. Venus is not simply a failed copy of Earth. It is a complete system with its own rules, its own balances, and its own long history. It holds warnings and lessons that apply beyond our solar system, where many exoplanets sit close to their stars and may share similar traits. A mission to Venus must plan for light, heat, and chemistry. Spacecraft use thick insulation, reflective surfaces, and careful paths to protect themselves. Orbiters map the surface with radar that can see through clouds. Probes dip into the air to measure gases and particles. Landers test materials against pressure and heat, even if only for a short time. Each dataset adds to a wider picture: how air moves, how the ground holds heat, how chemicals cycle, how the planet breathes its harsh breath. The travel is measured in months. The understanding may take generations. That is not a reason to pause. It is a reason to keep going, to place new instruments in better orbits, to test new ideas about winds, heat, and rock, and to compare models with real measurements. The closer we look, the more clear it becomes that small differences in distance from the Sun and early conditions can lead to very different outcomes. Mercury shows how to arrive by letting go of speed, learning patience, and working with gravity rather than against it. Venus shows how a bright, cloud-wrapped world can hide a deep physical truth about climate and feedback. Both demand careful paths and careful minds. Both reward endurance. A path inward begins with timing and ends with a set of orbits that let us measure and learn. Months for a flyby, years for a stable orbit at Mercury, a few months to cross to Venus when the window opens. These are not long spans on a cosmic scale, but they are long enough to require steady plans, long enough to remind us that travel between worlds is not a straight line. It is a set of arcs drawn by gravity, adjusted by short bursts of thrust, and designed to trade energy for time or time for energy as needed. Close to the Sun, light is sharp, heat is intense, and every move matters. Guidance is slow and careful. Thermal systems are strict. Navigation treats small numbers with respect. A tiny change in angle or speed can mean the difference between a clean encounter and a miss. The craft carries its own shade, its own clock, and the math that ties forces together. Mercury and Venus are near in distance, but different in nature. One is airless and fast, a metal-rich relic with a magnetic field. and long scars from a cooling core. The other is cloud-wrapped and slow-turning, with an air so thick it shapes the ground below and a heat that tests every material we can build. Both tell us what the inner solar system does to worlds over time. Both sharpen our tools for reaching farther. Mars is a dry world of rust-colored plains, thin air, and dust that moves in slow, whispering storms. It has been visible to human eyes since ancient times, a steady point of red that suggests land, weather, and history. Unlike Venus, which hides under cloud, Mars shows its valleys, canyons, volcanoes, and bright polar caps to any camera or telescope with a clear view. It is a planet we can map from orbit and imagine standing on. The idea of people living there is not only science fiction anymore, it sits at the edge of engineering and planning. The question is how long it takes to go and what the path requires. Mars does not keep a fixed distance from Earth. Both planets move around the Sun at different speeds and in stretched or elliptical paths. At its closest, Mars can come within about 34 million miles of Earth. At its farthest, it can be more than 250 million miles away. A spacecraft cannot leave on any day and expect a short trip. Departure must match a repeating pattern called a launch window. This window opens about every 26 months, when Earth and Mars line up on the same side of the Sun, so that a transfer path is efficient. When the timing is right, mission planners often choose a Hohmann transfer. This is a smooth, curved path that touches two orbits with the least energy. Launched at the proper moment, a spacecraft leaves Earth's orbit and enters a larger solar path that reaches Mars's orbit at just the time Mars arrives there. The travel time for this route is usually about 6 to 9 months. It is not a straight shot through space. It is a controlled fall along the Sun's gravity, using motion that Earth already gives to carry the craft outward until Mars's pull takes over. Life on board during such a cruise is quiet and careful. Astronauts would move farther from Earth than any humans before them. The blue disk would shrink to a bright point. Radio messages would take minutes to cross the gap. The crew would work on a time delay, planning tasks, sending reports, and waiting for replies that cannot arrive instantly. Schedules become longer and more deliberate. Systems must run with few errors and simple fixes, because help is far away. As the ship closes in, Mars grows from a star-like point to a small disk, and then to a full world with texture. The thin atmosphere, less than 1% of Earth's surface pressure, offers only weak braking for a landing and little shield against radiation from the Sun and deep space. The surface tells a longer story. Dry river channels cut across old plains. Minerals that form in water are locked in rocks. Ice sits at the poles and hides under soil in many regions. Mars once had liquid water on its surface. It may have had lakes and even shallow seas. These facts place two goals in front of us: search for past or present life, and learn what is needed for people to live there safely. The travel time itself depends on more than distance. If we launch outside the best window, fuel needs grow, and arrival times stretch. A mistimed start by even a few days can require a much larger push from engines to correct the path. Mission designers use detailed models of the solar system to set the date and hour of launch years in advance. They simulate where Earth and Mars will be and how much energy is needed to meet the target. This is not guesswork. The math is clear, and the motion of planets is reliable. Gravity assists can help, though they are used more often for outer planet trips than for Mars. A gravity assist is a close pass by a planet that changes a spacecraft's speed and direction without using fuel for that change. The craft falls into the planet's gravity well, speeds up, and leaves on a new path, borrowing a tiny amount of the planet's orbital motion. The planet slows by an amount too small to measure, but the spacecraft gains a useful boost. The best-known example is the Voyager program, a rare lineup of the outer planets, an event that happens about once every 176 years, let Voyager 1 and Voyager 2 move from Jupiter to Saturn and beyond, each time using a large planet to bend and speed their routes. Without those assists, the mission would have required many decades more, or fuel tanks larger than the craft. For Mars, the main tool is still the launch window and the Hohmann transfer. Some missions adjust this plan. They may choose a faster route that burns more fuel to cut weeks from the trip, or they may choose a slower, lower energy path to pack more mass into the spacecraft. Every design is a trade between time, fuel, payload, and risk. The goal is to arrive with enough speed control to enter orbit or begin a landing sequence, not to flash past. Entering Mars, orbit, or landing needs careful steps. The thin air makes heat shields still useful during entry, yet not strong enough by themselves to slow a heavy craft to safe speeds. Parachutes help, but they must open in a low-density atmosphere and survive supersonic flow. Rockets often finish the job close to the ground. Robotic landers and rovers have used combinations of heat shields, parachutes, retro-rockets, and sky cranes to reach the surface. Human landers will likely be larger and will need precise control and more fuel. The timing of arrival is also chosen to avoid global dust storms that can rise and darken the sky for weeks, affecting solar power and visibility. Radiation is a steady factor. The spacecraft must shield its crew during the months between worlds. Materials, water tanks, and layout can reduce exposure. Solar storms can add sudden bursts of charged particles. On Mars, the lack of a thick atmosphere and a global magnetic field means that habitats may need to be buried under soil or built with protective shells. Energy can come from nuclear systems or from solar panels paired with storage for long, dusty periods. The idea of people on Mars extends beyond a single landing. It includes supply systems, return fuel, and places to live and work. One plan is to produce oxygen and methane on Mars, using local resources, ice for water, and carbon dioxide from the air, so that a return vehicle does not have to carry all its propellant from Earth. Another plan is to send cargo ahead on slow, low-energy flights in earlier windows, building up supplies before a crew arrives. Each step reduces risk by dividing the task into parts that can be tested and improved. Time on Mars moves differently in small ways that matter to daily life. A day, called a sol, is about 24 hours and 39 minutes. That is close enough to Earth's day to keep a steady routine, with minor adjustments. The gravity is about 38% of Earth's, which changes how people move and how machines handle loads. Dust can coat equipment and windows. It is fine and sticky, so filters and seals must be designed with care. Temperatures swing widely between day and night, and the air is so thin that heat leaks away quickly. None of these challenges change the basic travel time under the best conditions. 6 to 9 months for the cruise, when launched during a good window every 26 months. The widespread in Earth-Mars distance explains why these windows matter. At poor alignments, even a powerful rocket cannot create a short, efficient path. The sun's gravity sets the rules. We work within them by picking the right day and the right curve. Mars asks for patience and accuracy. The flight is not long on a cosmic scale, but it is long enough to require discipline and robust systems. The approach, the braking, and the landing all happen in a short sequence where numbers must be correct and hardware must respond exactly as planned. The surface then offers science in many forms: drilling for ice, reading layers in ancient lake beds, measuring gases in the air, and listening for small quakes with seismometers that reveal the planet's interior. For human crews, the meaning of the journey is practical. It shows whether we can keep people healthy and productive far from Earth for many months. It tests closed life support systems, food growth, recycling of water and air, and medical care with limited tools. It teaches how to live with time delays and how to plan work that does not depend on quick messages. It also turns Mars from a distant target into a place with weather reports, maps, supply depots, and safe zones. The path to Mars is made of 3 ideas: use launch windows to reduce energy, follow efficient transfer orbits to cut travel time, and arrive with the ability to enter orbit or land safely in thin air. Gravity assists add options for some plans, but they are a bonus, not a requirement, for most crews bound for Mars. The rest is steady engineering: protect against radiation, manage heat and power, design for dust, and test each system until it behaves the same way every time. Mars remains a reachable world with a clear schedule. Every 2 years, and a little more, the window opens. In good conditions and with a proven path, the crossing can be done in half to 3/4 of a year. What happens after touchdown will depend on how well we prepared before leaving. The planet offers solid ground, useful resources, and a climate that, while cold and dry, does not crush or burn equipment within minutes. That is why Mars is the next step for long-term human presence beyond Earth. It is far, but not unreachable. It is hard, but not impossible. The travel is measured in months. The work that follows is measured in years. Between Mars and Jupiter lies a wide band of old rock. It is not a maze of tumbling boulders. It is a thin spread of bodies moving in broad orbits, a museum of fragments left from the solar system's youth. The asteroid belt stretches across hundreds of millions of miles. Long ago, these pieces might have gathered into a small planet. Jupiter's gravity kept that from happening. Its pull stirred the region and broke calm patterns that would have allowed the fragments to merge. What remains is a record of early ingredients: rock, metal, and ice that have changed very little since the first days. Crossing this region is less about dodging hazards and more about reading history. The average distance between sizable asteroids is so large that a spacecraft can pass through the belt without meeting a single rock. Space is the main feature here. The emptiness is honest. Instruments register points of light that move on predicted paths. Some tumble slowly. Some keep one face to the sun in a steady rhythm. The belt is not a graveyard. It is a library. Each object holds clues in its minerals, trapped gases, and impact scars. Carbon-rich bodies may carry water bound inside their minerals. Metallic bodies hold iron and nickel in concentrations richer than common ores on Earth. If future missions need water for fuel or life support, or metals for building, the belt offers sources that do not have to be lifted out of Earth's gravity. Time has a different quality in the belt. There is no weather, no sound, no dawn or dusk in the way we know them. The sun is a bright disk on a black background. Stars stand fixed to the eye. The slow change is orbital motion, measured in weeks and months as one object drifts relative to another. Each pass near a target is planned well ahead. Trajectories are adjusted with small burns. A radar ping, a camera sweep, a spectrum readout, simple actions carried out with care because there is no second attempt once the craft has moved on. Ceres comes into view on the long arc through the belt. It is the largest body here, close to 600 miles across, rounded by its own gravity, and classed as a dwarf planet. Its surface shows dark ground and bright spots that reflect sunlight strongly. Those bright spots are salts laid down by briny liquids that reached the surface and dried. Under the crust lies water ice and, in some areas, brine that may still move in pockets. The idea of a hidden ocean is debated, but Ceres clearly keeps water locked inside. That alone sets it apart in a region once thought to be only dry stone. Vesta shows a different path. It is not round, but large enough to be layered inside like a small planet. It once had a hot interior and volcanic activity. Its surface holds basalt, the same kind of rock that flows from volcanoes on Earth and the Moon. A giant impact near its south pole blasted out a deep basin and sent shards into space. Some of those fragments fell to Earth as meteorites. We have held pieces of Vesta in our hands, matching their chemistry to data from orbit. Most bodies in the belt are much smaller, rubble piles held together by gravity, dark, carbon-rich rocks that record the chemistry of early space dust, bright, stony objects with tight grain, metallic remnants from larger bodies that were shattered long ago. Each type answers a different question. How quickly did water reach the inner system? How did heat move through small worlds? How did impacts change their shapes and spin rates? A quick crossing of the belt takes months, but even brief flybys collect data that fill gaps in those stories. The hazard here is less about collision and more about isolation. A failure in this region leaves a spacecraft with no easy rescue, so navigation remains conservative. Courses avoid crowded paths near families of fragments. Star trackers keep steady log. Communications relay through wide antennas and patient schedules. The craft carries its own certainty forward by checking and rechecking simple numbers. Time to next burn, angle to target, rate of drift. Leaving the belt is not a sudden event. The sun grows a little smaller. The solar wind feels thinner. Dust levels drop. A change in the background of charged particles hints at a new domain. Jupiter's influence begins to rise. Even before the planet shows as a disk, instruments record subtle shifts, small tugs in trajectory, changes in the timing of signals, hints of a strong magnetic field far ahead. The craft is entering the realm of a giant. Travel time to Jupiter depends on the path. A direct, fast trajectory pushed by a powerful launch can reach the planet in a little over a year, as New Horizons did on its way to Pluto. Paths that use gravity assists from inner planets can take 4 to 6 years. Galileo used that method on its journey, building speed with flybys to arrive ready for orbit. Juno did the same, looping past Earth to gain energy before heading outward. The long routes offer fine control at arrival. The short routes deliver quick encounters. Both end at the same place, Jupiter's deep gravity well. Jupiter holds more than twice the mass of all the other planets combined. It is not a star, but it is a massive gas world, still warming as it slowly contracts under its own gravity. It shines faintly in infrared light, radiating more energy than it receives from the Sunday. As the craft draws near, colored bands fill the view, brown, cream, and rusty red, arranged in belts that circle the planet. The bands are jet streams, moving in opposite directions. Between them, storms rise and sink. Cloud tops show structures that span thousands of miles. The scale is hard to accept at first glance. Jupiter's diameter is about 11 times that of Earth. A clock on board will tick at a slightly different rate near the giant compared to far away. The effect, called gravitational time dilation, is small for a spacecraft, but it is real and measurable. It shows that strong gravity curves, not just paths in space, but the flow of time. the magnetic environment grows intense. Jupiter's magnetic moment, the measure of its magnet's strength integrated over size, is tens of thousands of times Earth's. Near the planet, the field is far stronger than Earth's field at the surface, and it traps high-energy particles in belts that can damage electronics. Flight paths are planned to reduce time in those belts. Shielding and smart operations do the rest. Jupiter has no solid surface where a spacecraft could land. The upper cloud deck is made mostly of ammonia crystals. Below that, clouds of ammonium hydrosulfide and water appear in models and in indirect measurements. Deeper still, hydrogen gas becomes so compressed that it behaves like a liquid. Go farther, and it becomes metallic hydrogen, a phase where electrons can move freely, allowing currents and magnetic fields to grow. Pressure and temperature rise to levels that cannot be replicated in full on Earth. The planet is a laboratory for physics under extremes. The moons turn the Jupiter system into a miniature solar system. Io, the inner large moon, is driven by tidal forces that knead its interior and keep it hot. It erupts with sulfur-rich volcanoes that can throw plumes hundreds of miles high. Europa holds a global ocean under an ice shell. Cracks and bands in the ice show where the surface has shifted over time. The ocean is kept liquid by heat from tides and the planet's own energy, and it may be in contact with rock at the seafloor, offering chemical gradients that life could use. Ganymede is the largest moon in the solar system and has its own magnetic field. Callisto is older and more cratered, with a layered interior and signs of buried ice. Each moon is a world with special rules. Each has a role in shaping Jupiter's environment through dust, gas, and electric currents. For missions that continue to the outer planets, Jupiter is also a tool. A gravity assist or slingshot near Jupiter can reshape a spacecraft's path and add speed without burning fuel for that change. The idea is simple. The craft falls toward Jupiter, gains speed, swings behind or beside the moving planet, and leaves in a new direction with a higher speed relative to the Sunday. The energy comes from Jupiter's orbital motion. The exchange is tiny for the planet, but large for the craft. Voyager 1 and Voyager 2 used this method after launching in 1977, taking advantage of a rare alignment that happens about once every 176 years. With careful timing, they visited Jupiter, Saturn, and then split paths, one to Uranus and Neptune, one upward out of the plane. Without Jupiter's assist, those tours would have taken far longer or required more fuel than the rockets could have provided. The slingshot requires precise geometry. Too close, and the spacecraft faces intense radiation and strong gravity gradients. Too far, and the gain is weak. The corridor for best results is thin when measured against the planet's size. Navigation teams aim for it with small course corrections made months ahead, when a short burst of thrust can shift the later path by thousands of miles. The moment of closest approach is brief. The planet fills the frame. Instruments record fields, particles, and images in quick sequences. Then the craft is on a new line, its speed relative to the Sun raised by the planned amount. For orbiters, the arrival is different. The goal is to slow down at the right moment so that Jupiter's gravity will capture the craft. A main engine burn turns a fast flyby into a long stay. Juno, for example, used a polar orbit to map the gravity field, sound the deep atmosphere with microwave instruments, and measure the magnetic field close in. A polar path avoids the worst of the radiation belts for part of each orbit and allows a full scan over many rotations. Data reveal that ammonia moves in giant cells, that belts and zones extend deep below the clouds, and that the magnetic field is lumpy and complex compared to Earth's. The Great Red Spot draws attention on every pass. It is a huge storm in the southern hemisphere, an oval that has lasted for centuries. Its winds reach several hundred miles per hour around the rim. The color comes from chemicals altered by sunlight and the planet's environment, though the exact recipe is still studied. Juno's measurements show that the storm extends deep below the visible clouds, hundreds of kilometers, suggesting strong roots in the atmosphere. Over recent decades, the spot has slowly shrunk in length and grown a little taller, changing shape into a more compact circle. Whether this is a slow decay or a cycle is not yet clear. Around the red spot, jet streams flow east and west, feeding and shearing the storm. Smaller vortices form and merge, plumes rise and collapse, lightning flashes within cloud decks. On Earth, a storm ends when it loses heat supply or crosses land or cold water. On Jupiter, there is no land to tear a storm apart, and internal heat continues to drive motion from below. The time scale is larger. Weather is measured in years and decades. The storm is not a single event. It is a standing feature in a living atmosphere. Radiation belts shape how close an orbiter can go and for how long. Charged particles move along field lines and are accelerated by the spinning magnetic field. Electronics are shielded and put inside protective vaults. Orbits are chosen to thread lower radiation lanes. Instruments are cycled to reduce exposure. Each close pass collects a set of measurements that add to maps of gravity and magnetism, helping to infer what lies below. Jupiter's pull also shapes the space around it on a large scale. The magnetosphere, the region dominated by its magnetic field, extends far beyond the planet, swelling on the day side and trailing off like a long tail on the night side. The size is so large that it would dwarf the Sun if made visible in the same units. Particles from Io's volcanoes add sulfur and oxygen to this environment. Electric currents link moons and the planet, producing auroras at the poles that are far more energetic than Earth's. Those polar lights are not only pretty arcs, they are signs of strong processes that tie together rotation, magnetism, and plasma flows. While instruments watch the planet, cameras and spectrometers sweep across the moons. Europa's surface shows long lines and bands where ice broke and refroze. Plumes of water vapor have been reported near its limb in some observations, rising from cracks and falling back as fine snow. Ganymede's grooves in bright lanes mark old tectonic patterns in ice. Callisto's old surface preserves impact histories from early times. Io's hotspots glow in infrared as new lava rolls out over older plains. Each observation is placed into a simple chain of understanding. Heat from tides, chemistry from rocks and water, energy from rotation and gravity, structures built over long spans. The idea of sending landers or ocean probes follows naturally. For Europa, the route is careful. Astrobiology requires strict protection. A lander, or a drill, must not carry Earth microbes into a potential habitat. Thick ice stands in the way of direct sampling of the ocean. Future tools may use heaters, mechanical drills, or tiny melts that follow cracks. Until then, orbiters measure the magnetic signatures that come from a salty ocean interacting with Jupiter's field and read the surface chemistry for signs of materials that rose from below. As a navigation tool, Jupiter remains a gateway. A craft bound for Saturn, Uranus, or Neptune gains more than just speed from a slingshot. It also gains a better angle for its next path. The solar system is three-dimensional. Orbits lie near the same plane, but not exactly on it. Jupiter's assist can tilt a craft's plane or flatten it, depending on approach. This allows designers to reach targets that would otherwise demand extra fuel. Numbers guide the work. Typical arrival times range from a little over a year for a fast flyby to several years for a complex fuel-saving route. The scale of the planet, roughly 11 Earth diameters wide, sets the visual experience. The strength of its magnetic environment sets the engineering choices. The depth of its weather sets the science goals. None of these facts stand alone. They link to form a picture of a system where gravity, gas, and time combine to make patterns that repeat and patterns that change. The region between Mars and Jupiter holds the raw pieces of rocky worlds. Jupiter holds the power to shape paths, drive weather, and form a family of moons that show nearly every kind of planetary process in one place. Moving from one region to the other is like stepping from a quiet archive into a large machine room. The pace of events, the energy levels, and the scales all rise. A spacecraft that has crossed the belt and reached Jupiter carries a record of that change in its data. Spectra of dark carbonaceous asteroids, radar profiles of rough metallic bodies, images of crater chains, maps of salts on Ceres, and then, later, gravity fields, magnetic lines, and cloud patterns from the giant. The same instrument platforms serve both ends, pointing, measuring, timing, and sending the results home through a narrow radio beam. The path onward uses what has been learned. If the craft is a flyby mission bound for the outer system, the next target is chosen to maximize science within the limits of power and time. If it is an orbiter, the course is shaped to add new angles on the belts, zones, and storms without exceeding radiation limits. The Great Red Spot will be seen again from a different height, the bands crossed at new longitudes, the moons passed at safer distances with better lighting. Each return builds on the last pass. Each result tightens the models that predict winds, currents, and fields. The belt and the giant, together, form a natural lesson in how our system grew. Small pieces that never became a planet mark the boundary of the warm inner zone. A large gas world marks the start of the cold outer zone. In between lies the gap that future missions fill with numbers and images. The crossing and the arrival are parts of a single exercise. Move with gravity, choose quiet, efficient lines, and let careful measurements replace guesses. Beyond Jupiter, sunlight thins to a pale glow, and distances lengthen into years. Saturn enters the frame with a bright rim before the globe is clear. The rings catch weak light and scatter it, so the planet announces itself by reflection first, then by form. Travel here takes patience. A careful route using gravity assists and efficient burns can still require most of a decade. Cassini's path is a plain example, nearly 7 years from Earth to orbit, with time traded for mass and safety. Speed alone is not the goal. Arrival with the right angle, the right fuel margin, and the right timing for science passes matters more than a fast clock. Saturn differs from Jupiter in tone and texture. Where Jupiter looks heavy and muscular, Saturn appears lean and balanced. It is the second largest planet, yet the least dense. Averaged out, its bulk would float in water. The upper atmosphere shows bands like Jupiter's, but with softer contrasts and a golden cast, winds can exceed 1,000 miles per hour along jet streams that circle the globe. Beneath the cloud tops, pressure drives hydrogen through phases, gas to liquid, and deeper still toward metallic behavior that carries current and helps form the magnetic field. Saturn, like Jupiter, emits more energy than it absorbs from the sunday. Slow contraction supplies heat from within. That internal source powers weather that does not depend only on sunlight. The rings hold attention even as instruments study the planet. They span roughly 175,000 miles from inner to outer edge, yet in most regions they are extremely thin, often on the order of tens of feet. Seen edge-on, they nearly vanish. Up close, the single ring resolves into many narrow ringlets. Each ringlet is a crowd of ice-rich particles mixed with darker rock, moving on tracks set by gravity. Sizes range from dust to boulders, and, in rare cases, mountain-scale chunks. Collisions are common, but gentle by space standards. Particles bump, chip, refreeze, and settle back into orderly lanes. Small moons, known as shepherds, objects like Pan and Daphnis, patrol gaps and edges, their gravity carving sharp borders and waves. Resonances with larger moons set up patterns that ripple through the material. Meteoroid hits and slow-moving disturbances that travel as spiral waves. The result looks delicate from a distance and engineered up close, but it is only gravity and time at work. Brightness comes from clean ice. Ring particles reflect much of the light that reaches them, which is why the rings show up so clearly despite Saturn's great distance. They are likely not permanent features on geologic timescales. Dusting by micrometeoroids darkens them over time, and measurements suggest a slow loss of material into the planet, a ring rain of tiny grains guided by electric and magnetic effects. Whether the rings formed from a shattered moon or from leftover material that never gathered into a single body remains under study. Either way, they are active rather than static, shaped by regular forces that can be measured, modeled, and tested across orbits. Saturn's magnetosphere traps charged particles and lights the poles with auroras. The magnetic field is weaker than Jupiter's, but still strong enough to matter for spacecraft design and operations. Radiation belts and ring dust require cautious flybys and robust shielding. Cassini managed years in this environment by choosing orbits that threaded safer lanes, diving above and below the rings to map gravity and structure while avoiding long exposures to harsh regions. Those paths produced detailed profiles of winds, temperatures, and composition, and revealed fine structures, ringlets, propeller-shaped gaps from embedded moonlets, and seasonal changes. Saturn's system is a family. Titan dominates the outer moons by size and scientific pull. It is the only moon in the solar system with a thick atmosphere, mainly nitrogen with traces of methane and organics. Sunlight at Saturn's distance is about 1% as bright as at Earth, so photochemistry works slowly, building a high orange haze that scatters light and cools the surface. Temperatures hover near 179 degrees Celsius. Water is rock hard and forms the bedrock. Methane and ethane behave like water does on Earth. They evaporate, condense, and fall as rain. Rivers carve channels and feed lakes and seas. Winds shape long dunes of hydrocarbon grains. A full Titan day matches its orbital period around Saturn, about 16 Earth days, which stretches the rhythm of light and dark into long intervals. Reaching Titan follows capture at Saturn first. Weeks of orbital adjustments bring a spacecraft into the right plane and speed to meet the Moon. Entry through the atmosphere takes hours from the top of the haze to the ground. Parachutes do the heavy work early, then smaller devices and perhaps brief propulsion settle the lander near a chosen site. The atmosphere's density reduces impact energy and protects the surface hardware from extreme thermal loads, but the cold demands robust heaters and careful materials. Gravity is about 14% of Earth's easing lander design and making movement slow and buoyant. Sound is muffled by the thick air. Light is dim but steady. A camera would see an amber sky and pale landscapes, icy plains, dark lake surfaces, and bluffs cut by channels. In rare breaks in the haze, Saturn's rings can show as thin, bright arcs. Titan's value runs in two directions. On the surface, it offers a working example of climate with a different solvent. Methane takes water's role, so familiar processes, clouds, rain, erosion, waves appear with different chemistry and speed. Below the ice, models and measurements suggest a global ocean of salty water. Tidal flexing and heat from radioactive decay may keep that ocean liquid. Organics formed in the air settle over time and could be carried downward by cracks or impact events, mixing with water at depth. That combination energy, liquid water, and organics puts Titan in the small group of places where life's basic requirements might be met. Any mission plan accounts for this by following strict planetary protection steps to avoid contamination and by designing instruments that can tell biological signals from non-biological chemistry. Enceladus, far smaller than Titan, changes priorities the moment its plumes come into view. Near its south pole, fractures nicknamed tiger stripes vent water vapor and ice grains into space. A spacecraft can fly through the plume and sample it directly. Instruments have detected salts, simple organics, silica grains that point to hydrothermal activity, and other markers that suggest a warm ocean inside the moon in contact with rock. Enceladus extends Titan's story. Where Titan shows a surface solvent cycle in the cold, Enceladus offers access to subsurface water and chemistry linked to rock and heat. Together, they make Saturn's system central to questions about habitability beyond Earth. Operations near the rings reward slow, methodical passes. Orbits can be adjusted to skim just above the ring plane and then swing over the poles, letting instruments build three-dimensional maps of fields and particles. Gravity mapping reads density beneath clouds. Microwave instruments sense deep ammonia structure. Infrared spectrometers trace temperatures and ices. Radio science measures tiny tugs that reveal internal mass distribution. These tools showed that Saturn's interior is layered, that differential rotation extends below the visible atmosphere, and that the ring's total mass is lower than would be expected if they were ancient and unchanged. They also revealed small, time-varying wiggles in the rings, subtle waves driven by oscillations inside Saturn itself, turning the rings into a kind of seismograph for the planet. Travel times to Saturn reflect design more than distance alone. Direct flights with large launch energy can arrive in a few years, but leave less margin for heavy payloads or large insertion burns. Gravity assist paths from Venus, Earth, or even Jupiter add years, but lower the required fuel for the spacecraft to stop at the target. For probe delivery to Titan or Enceladus, schedules add more weeks for phasing, safe approaches, and lighting conditions. These choices are practical. Long missions can carry more instruments and plan more encounters, while short missions give quick snapshots. Both approaches require accurate navigation, radiation planning, and thermal control in a cold, low sunlight environment. The rings themselves are a working lab for orbital mechanics. In resonant zones, particles bunch and gap. Edge waves roll where a moon's gravity tugs rhythmically. Vertical warps appear near inclined moon orbits. At small scales, collisional physics sets the size distribution of grains. At large scales, the cumulative effect of billions of interactions yields smooth surfaces and clean edges. Light scattering off rough, icy grains produces features that change with viewing angle and sun angle, which is why the rings can glow strongly at certain geometries and dim at others. The same physics helps interpret debris disks around other stars, where direct imaging shows broad rings shaped by unseen planets. Saturn's weather shows its own character. Great storms appear about once a Saturn year, roughly 30 Earth years, and can encircle the planet, leaving long-lasting cloud streaks. A persistent hexagonal wave at the North Pole marks a standing pattern in the jet stream, likely driven by a combination of winds and planetary rotation. Lightning has been recorded within storm systems, and temperatures vary with season as the planet's tilt changes sunlight on the two hemispheres. The rings also cast seasonal shadows on the atmosphere, influencing local temperatures. These links between rings and weather highlight how one part of the system shapes another. Instruments watching the poles see auroras that pulse and change shape, tied to the solar wind and to the planet's rotation. Radio emissions trace processes in the magnetosphere. Dust detectors pick up grains from embedded moonlets and from meteoroid hits. Fields and particles sensors map space weather through the system. Every pass adds a layer of detail. Over months and years, the pieces combine into a coherent picture, a gas giant running on internal heat, wrapped in rings that are thin but wide, and orbited by moons that demonstrate different paths to complexity. The practical steps to operate here remain straightforward despite the beauty. Keep radiation within hardware limits. Manage power with distant sunlight or with radioisotope sources. Use frequent small trajectory corrections far from targets and few large burns close in. Plan flybys to protect instruments from dust and charged particles. Calibrate often in the cold to hold measurement accuracy. Send data steadily through narrow radio links that must cross nearly 1 billion miles, adjusting bit rates as geometry changes. Time in Saturn's realm is counted in orbits. Ring particles circling in hours, inner moons moving in days, Titan looping every 16 days, seasons unfolding over decades, ring evolution measured in much longer spans. A spacecraft fits into this clock by repeating tracks that shift slightly each pass. The rings that looked like a single band on approach resolve into layers. The planet that seemed smooth reveals wind, wave, and structure. The moons that were points become places with shorelines, vents, and ridges. Each refinement comes from simple actions done at the right time point. Measure, adjust, repeat until models match. Observations and predictions hold. Standing above the rings, a camera sees brightness that belies distance. The thinness of the material and the clean ice surface work together to turn faint sunlight into a broad sheet of light. Below, the planet reflects some of that glow back, and the two surfaces, ring plane and cloud top, light each other. In the shadowed regions, stars are sharp and undisturbed by air. The quiet is not an emotion, but a condition. There is no medium to carry sound, no breeze, only motion along calculated lines. Saturn's place in a journey outward is both target and tool. It is a complete world to study, and, at the same time, a junction where paths can bend toward Uranus, Neptune, or beyond. A well-planned swing-by can add speed and adjust inclination without a drop of propellant for that change. An orbiter can thread high-latitude routes to sample polar fields and then drop to the ring plane for close passes. Lander concepts for Titan and sample ideas for plume fly-throughs at Enceladus. Extend the system's reach from remote sensing to direct contact. The distance from Earth to Saturn does not hide the system's logic. Numbers connect the parts. Ring thickness in tens of feet. Ring span in hundreds of thousands of miles. A Titan day matching 16 Earth days. Sunlight at 1/100th of Earth's intensity. Surface cold at 179 degrees Celsius. Low gravity at 14% of Earth's winds, near 1100 miles per hour, high in Saturn's atmosphere. Each figure earns its place because it explains behavior. Thin rings can cast sharp shadows. Dim light slows chemistry. Low gravity alters lander design. Cold locks water into rock-hard ice, while methane remains liquid. Fast winds arrange clouds into bands and waves. Far from the inner planets, the pace slows by necessity and design. Schedules stretch over seasons. The craft's systems cycle through work and rest as geometry allows. What begins as a long flight ends as a steady pattern. Approach, measure, analyze, adjust, repeat. The reward is clarity. Saturn's calm appearance hides a dynamic interior and an active family of moons. The rings, bright and thin, are not a decorative edge. They are a physical record that can be read. Titan and Enceladus are not footnotes. They are central to the question of habitability in cold places. Each orbit refines that picture with simple, careful steps. Past Saturn, light thins and the clock slows. The spacecraft settles into a careful routine. Long cruise segments, short checkouts, instruments resting to save power, heaters cycling to keep lines and tanks within limits. The sun becomes a bright lantern rather than a warm disk. Solar arrays alone are no longer enough. Radioisotope power or deep hibernation fills the gap. The path to Uranus is measured in years, often 7 to 10 with gravity assists and patient navigation. Course updates are rare and deliberate, sent across a span so large that radio messages need hours to make the round trip. Guidance shifts from constant hand-holding to trust in the trajectory. Uranus waits on a wide, cold orbit with a tilt that sets it apart. Most planets lean a little. Uranus is tipped almost onto its side, about 98 degrees. That tilt turns seasons into long chapters. Each pole spends about 42 Earth years in sunlight and then 42 in darkness. A full Uranus year is 84 Earth years. Morning and evening move at a pace that stretches human intuition. What we call a season at home becomes an age here. Approach begins with small changes. The pull from Saturn fades, and a new gravity field starts to guide the track. The planet shows as a pale blue disk with faint rings and a family of small moons. The color comes from methane high in the atmosphere, which absorbs red light and leaves a blue cast. Uranus is an ice giant rather than a gas giant, which means water, ammonia, and methane ices make up much of its interior, layered above a core we still study through indirect measurements. There is no solid surface to stand on. Gases thicken downward into hot, dense fluids under high pressure. Travel here rewards endurance. Systems survive by cycling. Electronics spend long stretches in sleep. Heaters and valves do the slow, quiet work that keeps a craft alive. Teams on Earth plan for a mission that will outlast jobs and rotations. People who launch the spacecraft may be retired by arrival. The mission becomes a relay across time, with procedures and software handed from one group to the next. As the spacecraft swings into the Uranus system, rings resolve into narrow, dark bands. They are far dimmer than Saturn's, made of larger, darker particles with gaps set by resonances. Winds at high levels can exceed 500 miles per hour, but the planet looks calm from a distance. Its features low contrast and smooth. Energy from the sun is weak here. Weather responds more to slow seasonal changes than to day-night cycles. The long tilt means sunlight pours onto one hemisphere for decades, while the other sits in deep shade. The line between day and night, the terminator, barely moves for years. Moons move along the tilted plane, their faces drifting in and out of light over decades. Titania and Oberon, Ariel and Umbriel, Miranda with its odd cliffs and patchwork terrain, each shows signs of ancient shifts and, in some cases, hints that liquid water may exist deep below ice. A subsurface ocean is not proven for all, but models allow it. Tidal heating from Uranus's gravity plus radioactive heat inside, can keep layers warm enough for liquid pockets. The extreme length of seasons sets surface temperatures and could drive slow cycles of freezing and thawing near the top few meters. Operations adjust to the slow rhythm. Imaging is timed for the best contrast near equinox, when sunlight reaches the equator and the atmosphere responds. Radio science listens for tiny tugs that reveal mass inside the planet and the moons. Magnetometers map a magnetic field that is tilted and offset from the planet's center, a sign of complex flows deep within. Microwave and infrared instruments watch heat patterns that change over years rather than days. Each pass adds a slice of data. Stacked together, those slices become a picture of a sideways world, shaped by time. A mission to Uranus asks for patience at every step. Navigation uses small burns long before arrival to place the craft on the right thread through the system. Communications trips take nearly 3 hours one way at these distances, so even a simple confirmation runs on delay. Fault protection has to be robust and quiet, able to keep the craft safe without constant contact. The reward is a clean view of an ice giant that has had only a single close visitor in our history. New measurements turn a smooth blue disk into a layered, working planet with weather, fields, and a set of moons that keep questions open about water and habitability in cold places. Beyond that orbit lies Neptune. Distances grow again, and travel times lengthen into the teens of years unless a mission uses a strong Jupiter assist. Even with that help, the scale is large. Voyager 2 needed 12 years to reach Neptune after launch in 1977. A comparable route today would be similar in length unless new propulsion is used. Out here, day and night mean little to a spacecraft. Power is a steady output from radioisotopes. Thermal control is the constant job. Instruments take turns to save power and bandwidth. Each transmission carries a slim thread of data across billions of miles, scheduled to match antenna time at Earth and the geometry of the link. Neptune shows a deeper blue than Uranus, again from methane, but with stronger contrast and faster weather. It is also an ice giant, but more active in its upper layers. Winds can exceed 1,300 miles per hour, the fastest measured in the solar system. Features appear and fade over months and years, with dark storms forming bands and spots that drift with latitude. A Neptune day is about 16 hours. A year is about 165 Earth years. Seasons change across decades. A storm seen on one pass could still be there years later, or it could have evolved into a different shape under the push of jet streams and internal heat. The interior follows the same broad plan as Uranus. Gases above, a mantle of high-pressure ices, below water, ammonia, and methane in forms that behave like superheated, super-pressured fluids and a deeper core of rock and metal. Under the pressures inside, water can enter an exotic state called superionic. In simple terms, oxygen atoms form a lattice, while hydrogen ions move through it, letting the material conduct electricity. Flows in these layers help generate a magnetic field that, as at Uranus, is tilted and offset from the center. The field interacts with the wind of charged particles from the sun to produce auroras and radio emissions. Neptune's rings are faint and dusty, with arcs short, bright segments held together by gravitational effects with nearby moons. Those arcs challenge simple models and show that even thin rings can have structure. The planet's largest moon, Triton, pulls attention quickly. It orbits backward relative to Neptune's spin, which suggests it is a captured body from the Kuiper belt. Its surface shows young plains and few craters in places, and Voyager 2 imaged geysers, likely driven by seasonal warming of nitrogen ices. Triton is cold, but active, An interior warmed by tidal forces could support layers of liquid water beneath an icy shell, linking it to the broader set of worlds, where heat, water, and chemistry meet. Approach and operations at Neptune draw on lessons from Uranus with added caution for fast winds and low sunlight. The path is set years in advance so that the craft can fly by in the correct plane to see key targets in good light, or to enter orbit if the design allows a large braking burn. A flyby sacrifices time for reach, covering a lot of ground quickly. An orbiter slows down to stay, but must bring more propellant or use clever aerocapture in the upper atmosphere, a technique that reduces speed by skimming through gas. Aerocapture is promising in theory, but has not yet been tried at an ice giant. Until it is, designs tend toward flybys or very careful high-energy orbiters. Science goals set the cadence. Cameras track storm systems to measure wind speeds by following clouds. Infrared instruments map temperatures across latitudes to see how seasons and internal heat shape the atmosphere. Radio occultation signals sent through the planet's limb to Earth reveal pressure and temperature with height. Gravity fields are mapped by tracking tiny changes in the spacecraft's speed as it passes near the planet and the moons. Magnetometers trace the field's shape and its changes with time. Dust detectors sample ring material. Each dataset fits into a framework that asks simple questions first. How fast? How deep? How bright? And then builds toward models that predict behavior. The moons at Neptune round out the system. Nereid follows a stretched orbit far from the planet. Proteus is irregular and dark. Triton dominates as a likely captured dwarf planet-like body, with an atmosphere of thin nitrogen and a surface marked by ices and smooth plains. Its retrograde path suggests that it arrived after Neptune formed, reshaping the system as it settled in. A mission that flies through Triton's faint atmosphere during an occultation or samples any plume material would test for complex chemistry linked to a warm interior. Between Uranus and Neptune, navigation is an exercise in accuracy over long spans. Tiny errors early become large misses later, so course corrections are best made far from the target when small burns have the most leverage. With round-trip light times of hours, autonomy on the spacecraft carries more weight. Fault management handles events without immediate help. Command bundles are checked and rechecked before uplink. Downlink schedules match Earth antenna availability and the planet's position in the sky. Numbers set context and stay simple. Uranus lies well over 1 billion miles from the Sun. Neptune is farther still. A message can take nearly 3 hours to reach Uranus and longer to reach Neptune. Typical cruise times are 7 to 10 years to Uranus with assists, and 12 or more to Neptune, depending on path and launch energy. Winds at Uranus reach hundreds of miles per hour. At Neptune, the fastest exceed 1,000. Uranus's tilt is near 98 degrees. A Uranus year is 84 Earth years. A Neptune year is 165. Each figure earns its place by explaining what we see: slow seasons, tilted magnetic fields, faint rings, fast jets, moons with stressed interiors. What changes most beyond Saturn is not only distance, but tempo. Planning extends across decades. Power budgets assume cold and dark. Science builds by layers rather than by quick campaigns. The reward is a clean separation of processes. With weak sunlight, internal heat, and deep dynamics become easier to isolate. With long seasons, the atmosphere's slow response can be tracked without daily noise. With tilted fields and offset dynamos, magnetic behavior can be mapped in ways that test ideas about how planets generate fields. Uranus turns the idea of a season into a long, steady state and shows that a planet can run sideways and still keep order. Neptune takes the same basic interior and drives faster weather, sharper contrasts, and an active, captured moon. The path between them measures patience in years and engineering in details. Heaters that never fail, clocks that keep time in the cold, valves that move after long sleeps, and radios that hold a link across billions of miles. Neptune is far from the Sun, but it is not quiet. As the spacecraft settles into orbit, the view is motion everywhere. Bands of cloud wrap the globe. Dark ovals form and fade. Bright, high clouds drift above deeper layers. The planet's blue color comes from methane, which absorbs red light and lets blue pass. Sunlight here is weak, yet the weather is strong. The main driver is heat from within. Neptune gives off more energy than it receives, over twice as much, so rising warmth fuels winds and storms that do not depend on day and night. Those winds are the fastest measured on any planet. They can reach about 1,300 miles per hour in the upper atmosphere. For comparison, a powerful hurricane on Earth is around 150 miles per hour. The difference resets our sense of scale. A feature can circle much of the planet in hours. From above, some storms look almost still because they are so large and the background is moving with them. The Great Dark Spot, first seen by Voyager, 2 inches, 1,989, is a type of high-pressure system that can appear for years and then vanish. Unlike Jupiter's red spot, which has lasted for centuries, Neptune's big storms come and go, suggesting complex layers and changing stability underneath. Between the dark systems, small white clouds made of methane ice form at high altitude. They cast thin shadows on lower cloud decks, letting us trace wind paths and wave patterns across wide areas. Waves ripple along jet streams. Vortices roll at the edges of faster flows. At deeper levels, temperatures rise and gases thicken into hot, dense fluids. There is no solid ground to stop a storm or break its structure. Energy travels up and down through the column, and rotation shapes the flow into bands that run around the planet. Sound does not carry to us. We see the speed and the shape, but we do not hear it. Instruments measure pressure, temperature, and wind by tracking cloud motion and by timing radio signals that pass through the limb of the atmosphere. Infrared maps show warm and cool zones. Microwave readings probe deeper, revealing how gases are layered. Over months and years, the same regions are revisited to see how features change with season and with slow shifts in sunlight. Neptune's day is about 16 hours, but seasons unfold over decades because a year lasts 165 Earth years. That slow pace means we compare images from one mission or observatory to the next to build a record. Neptune's magnetic field, generated by flows in conductive, high-pressure layers, is tilted and offset from the center. That geometry produces auroras and radio emissions that vary in ways different from those at Earth or Jupiter. Dusty rings circle the planet in faint bands, with short, bright arcs held together by gravitational effects near small moons. The largest moon, Triton, follows a backward orbit relative to Neptune's spin, a sign that it was likely captured from the Kuiper belt. Its thin nitrogen atmosphere and active geysers point to heat inside, probably from tides and radioactivity. Triton's surface shows young plains and few craters in places, which supports the idea of ongoing change in a very cold world. Beyond Neptune, sunlight fades to a bright star. The spacecraft leaves the region of the giant planets and crosses into a space where the sun's influence begins to thin. For billions of years, the sun has blown a steady outflow of charged particles called the solar wind. That flow stretches outward in all directions and carves out a large bubble, the heliosphere, that helps shield the solar system from much of the radiation that fills the galaxy. The outer part of that bubble is not a sharp shell. It is a broad zone where the solar wind slows and piles up against the gas between the stars. As the craft moves outward, it sees fewer solar particles and more high-energy cosmic rays from the galaxy. The slowing, heated solar wind region is the heliosheath. Past that lies the heliopause, the boundary where the pressure of the interstellar medium balances the pressure of the solar wind. Positions shift with the solar cycle and with conditions in the local interstellar gas, so the edge is not a perfect sphere. Crossing this region is slow. Communication delays stretch. Commands and data take many hours round trip. Solar panels would not work here. Power comes from radioisotope sources that produce steady electricity and heat. Only 2 spacecraft, Voyager 1 and Voyager 2, have crossed into interstellar space so far. Their signals now take over 18 hours to reach Earth, and yet they continue to send back measurements of fields, particles, and plasma waves. Their data show clear changes in charged particle counts, magnetic field direction, and plasma density at the boundary, proving that the heliosphere sits inside the larger medium of our galaxy. These records are not about pictures. They are about the shape and size of the sun's protective bubble and the nature of the space beyond it. Travel in this region is a test of endurance. With no close targets, the craft runs on a careful schedule. Long periods of quiet, brief sessions of measurement, steady health checks, all tuned to save power and keep systems stable. Temperature control keeps lines from freezing. Star trackers hold attitude with faint guide stars. Navigation uses infrequent updates because light time delays are long. The trip is counted in astronomical units, Earth-Sun distances, and in decades. Even so, the scale is local in galactic terms. At hundreds of AU, we are still very near the Sun when compared to the distances between stars. Far inside the heliosphere, but beyond Neptune's orbit, lies a set of small, icy worlds. Among them, Pluto stands out because it has been mapped well by a fast flyby. Pluto orbits in the Kuiper belt on a stretched path and is part of a binary system with its large moon, Charon. Reaching it is a long job. New Horizons, launched in 2006, used a Jupiter assist and arrived in 2015 after about 9.5 years and more than 3 billion miles of travel. The spacecraft could not slow down for orbit. It had hours to gather the best images and spectra, and then continued onward. The flyby revealed a world far more complex than expected. Pluto's surface includes bright plains of nitrogen ice, dark regions rich in complex organics, and mountains of water ice as hard as rock in the deep cold. The large heart-shaped feature, called Tombaugh Regio, contains a plain Sputnik, Planitia, with a smooth cell-like pattern caused by slow convection in thick nitrogen ice. The area reflects much light, which is why it stands out. A thin atmosphere of nitrogen expands when Pluto is closer to the Sun and collapses as it moves away, freezing onto the surface. Haze layers rise high above the ground, scattering the weak sunlight into a blue rim when viewed off to the side. Charon, nearly half Pluto's size, orbits so that the two bodies circle a point between them. The surface shows canyons and blocks, likely shaped by internal freezing and expansion of water ice, or by older tectonics. Together, the pair act like a small, coupled system, tidally locked to always show the same faces to each other. Pluto's year is 248 Earth years, which means the slow change of seasons spans many human lifetimes. The discovery of such variety in a small, cold world changed how we think about distant objects. Simple size and distance do not fix how active a body can be. Beyond Pluto, the Kuiper Belt continues with dwarf planets, small bodies, and comets. New Horizons has already visited another Kuiper Belt object, showing that contact binaries, two bodies gently joined, are common. Colors and reflectivity vary, telling us about surface chemistry, radiation processing, and collisional history. These objects preserve early solar system materials in cold storage. Studying them ties formation models to direct evidence: what ices and dust were present, how they were mixed, and how they have been altered by light and time. Past the Kuiper Belt lies the scattered disk and, farther still, the distant Oort cloud, a vast spherical reservoir of comets that likely extends tens of thousands of AU from the Sunday. No craft has reached those areas. Their existence is inferred from the orbits of long-period comets that drop inward from all directions. The step from planets to Kuiper Belt to Oort cloud shows a gradual fade rather than a hard boundary. The solar system does not end. It transitions into the galaxy. In all of these regions, time changes meaning. Near Earth, missions measure time in minutes and hours. Around the giants, time is measured in years and seasons. In the deep outer system, time is measured in decades of flight, and in the slow cycles of distant worlds. The practices shift to match. Plan ahead, save power, accept delay, keep instruments simple and steady. The same navigation principles still apply: small burns early, clean geometry at targets, and precise tracking, but patience becomes the main resource. Neptune's fast winds and transient storms show that weak sunlight does not mean weak weather. Internal heat and rotation can design their own climate. The heliosheath and heliopause show that the sun sits inside a larger environment that changes with the solar cycle and with local interstellar conditions. Pluto and its neighbors show that small, cold bodies can be active and layered, with thin air, moving ices, and surface renewal. Voyager's crossings show that a mission can leave the realm of planets and keep sending back clear signs of where the sun's influence yields to the galaxy. Beyond Neptune, the sun's light reaches us after more than 4 hours, and the idea of day and night loses its usual role. There are no regular horizons here, no immediate paths to orbit and land. The work becomes measurement over long spans, turning sparse data into firm conclusions. With simple tools and steady math, the edge of the solar wind is not a wall. It is a threshold defined by balance. Beyond it, the particles and fields belong to interstellar space. That space is thin, cold, and full of high-energy radiation, but it is also structured, with its own flows and magnetic patterns. Crossing it requires nothing more than time and power. The route outward ties the pieces together. Fast winds on a blue world shaped by inner heat, a fading solar wind pressed against the galaxy's gas, a small binary system with nitrogen, ice plains, and a thin sky, a belt of cold bodies that keep the solar system's early chemistry on file. And, at the limit of our reach so far, 2 small spacecraft sending back faint signals that prove a simple point. The solar system is part of something larger, and that larger place is not empty. It is a medium we can measure, step by step, with patient craft and clear questions. Time becomes the main obstacle as distances grow. Machines can wait. Humans cannot wait in the same way. A spacecraft can power down most systems, warm its lines with small heaters, and wake on schedule for checks. It can follow its course for decades with only minor corrections. A crew cannot simply idle through the same span without food, air, and the steady work of mind and body. This gap drives the idea of putting people into a controlled sleep for long voyages. The goal is not to freeze someone solid. It is to slow the body safely, reduce needs, and cut the strain of time. Researchers already cool patients for short periods in hospitals to protect the brain and heart after injury. Animals show that deeper pauses are possible. Some frogs and insects survive cold seasons by lowering metabolism until warmth returns. At smaller scales, we store cells, embryos, and tissues at low temperatures and revive them later. Spaceflight studies take the modest first step: induced torpor. Torpor is a state like natural hibernation. Body temperature drops a few degrees, heart rate and breathing slow. Muscle use is reduced. If a crew can spend most of a months-long cruise in torpor, the ship can carry less food and water and smaller life support units. Early concepts suggest large savings, tens of %, because sleeping bodies consume less oxygen and make less heat. The medical work is careful and slow. Cooling must be even and gentle. Fluids must not freeze. Electrolytes and blood chemistry must stay within safe ranges. Muscles need stimulation to avoid wasting. Bones need loading to limit loss in weak gravity. Waking cycles are planned. Short periods for exercise, checks, and any burns or navigation events that need human oversight. Habitats change to match. Quiet, dark pods replace large cabins. A central area supports exercise, hygiene, and medical care during wake windows. The ship's computers handle routine tasks, cool the crew when needed, and contact Earth on schedule. The risk is not only physical, there is a mental side. A person who sleeps through months or years will wake into a changed world. The crew will skip long stretches of experience, then catch up all at once. Memory anchors help. Messages from home, recorded logs, clear timelines, training covers, orientation after long sleep, and the slow return to normal activity. Ethics matter too. Consent must be clear. Medical safeguards must be strong. Decisions about who sleeps, when they wake, and who stays awake must be set by procedure, not by mood. Even partial torpor on early Mars trips will teach lessons that shape deeper missions. If the method proves safe, the same tools can extend human reach to the ice giants and beyond, not by going faster, but by making time less heavy for the people aboard. Speed still draws attention, because speed sets what is possible. The fastest thing we know is light. In vacuum, it moves about 186,000 miles per second. That is a constant of nature, not a feature of our engines. It sets the limit for how fast information and matter can travel. Even so, light takes time. The moon is just over a second away at light speed. The sun is about 8 minutes. Jupiter can be tens of minutes. Neptune is hours. When we look out, we always look back in time by a little or by a lot. Relativity explains more. When a ship moves close to light speed, time aboard slows compared with time on Earth. This slowing is not a trick of clocks. It is how the universe works. To someone on the ship, life feels normal. To people at home, the ship's time runs slower. Distances also shorten along the ship's direction of travel from the ship's point of view. These effects grow as speed increases. The price is energy. As a craft approaches light speed, the energy needed for each small increase rises sharply. Reaching 99% of light speed would require extraordinary energy and very efficient systems to shed waste heat. Reaching 100% is not possible for any object with mass. because the energy required would be infinite. Even so, light time gives useful yardsticks. A signal to Mars can take minutes, and to Neptune, it can take hours, depending on positions. Light from Alpha Centauri takes a little over 4 years. From the Andromeda Galaxy, it takes millions of years. These numbers show scale more than they show limits. They remind us that even the fastest messenger needs time, and that far targets are not far only in miles, but in years. If near-light travel for people is out of reach for now, better propulsion can still reshape the solar system. Chemical rockets are simple and strong, but they carry limited energy per pound of fuel. Nuclear fission, and especially fusion, promise higher energy density. Fusion is the process that powers stars. It joins light nuclei such as hydrogen isotopes into heavier ones and releases a large amount of energy. A fusion rocket would try to direct a portion of that energy into exhaust. Designs vary. Pulsed pellets, ignited by lasers or particle beams, magnetic nozzles to direct charged products, or hybrid systems that use fusion heat to drive a working fluid. In principle, fusion could cut a Mars trip to a few weeks and send heavy craft to the outer planets in a year or two. The hurdles are real. Stable ignition, fuel handling, shielding, and turning raw energy into smooth thrust without cooking the ship. Antimatter sits at the far end of the scale. When matter and antimatter meet, they convert almost completely into energy. In theory, milligrams can store an ocean of power. A drive that uses antimatter directly, or as a spark to trigger fusion, could reach very high speeds with compact tanks. In practice, making, storing, and using antimatter is hard. It must be held in magnetic traps, away from normal matter. We produce tiny amounts in labs. Losses turn into bursts of energy that must be confined. If the handling problem ever yields, antimatter could change mission planning from how much can we carry to how well can we control thrust and heat. Light sails take a different path. A sail does not carry fuel. It reflects photons from the sun or from a ground-based laser array. Light has momentum, so each reflection gives a small push. Over time, the pushes add up. For interplanetary trips, a large, thin sail can spiral outward from the Sunday. With lasers, a small sail can gain speed quickly near Earth and then coast. The challenge is building strong, light materials and pointing large laser systems for sustained periods without overheating the craft. The appeal is clear: no onboard propellant and a simple vehicle once the boost phase ends. Even bolder ideas pull from general relativity. The math allows space itself to stretch and bend. In principle, if a drive could compress space ahead of a ship and expand space behind it, the ship could move without exceeding light speed locally. The ship would ride a wave of geometry. This concept is often called a warp drive. It requires exotic conditions, negative energy densities, or special fields that we do not know how to make in the required amounts, if at all. Wormholes, which are shortcuts linking distant points, face similar issues. They are allowed by equations, but need matter and stability we do not know how to achieve. These ideas are not engineering plans today. They serve as targets for theory. They remind us that speed limits apply to motion through space, while geometry itself plays by deeper rules. Closer to hand, hybrids make sense. A fusion stage for the deep push, chemical thrusters for precise maneuvers, and electric propulsion ion or Hall thrusters for efficient, low-thrust spirals around planets. Electric thrusters use power to accelerate ions to high speeds, trading low thrust for excellent fuel economy. They are slow to start, but ideal for long hauls and fine shaping of orbits. A future flagship could launch on a chemical booster, spiral outward on electric drive, fire a fusion stage for a fast cruise, then enter orbit with aero capture or a final burn. Each piece has a clear job. All these systems must manage heat, radiation, and reliability. High-energy engines produce waste heat that must be rejected into space through radiators. Better radiators mean lighter ships or more power per pound. High-speed travel runs into dust and gas. Even a grain of sand can hit with great energy at a high fraction of light speed. Shields may need to be thick or smart electromagnetic fields to deflect charged dust, or thin sacrificial layers that vaporize safely. Guidance must work without constant help from Earth. This pushes autonomy, star tracking, hazard detection, and health management on board. Time keeps returning as the core design factor. If crews can sleep safely, the ship can move slower and carry less mass, making missions simpler. If engines can run hotter and faster, trips shrink into months or weeks, and sleep is less important. If both advances arrive torpor for people and high-performance drives, the solar system becomes a set of reachable places on human schedules. A Neptune mission could fit within a career. A tour of Kuiper Belt objects could be planned as a sequence, not as a once-in-a-generation event. Even at the limit of speed and endurance, light's travel time remains the baseline. Signals to a fast ship still take minutes or hours. Control by ground teams becomes guidance rather than steering. Crews train for independence. Procedures cover rare events as well as routine ones. The craft carries spares, printers for parts, and flexible software. In this way, human factors and propulsion grow together. Faster ships mean shorter exposure to radiation. Torpor means fewer supplies and lower stress. Better sails or engines mean new targets and richer science. Each gain supports the next. The change in mindset is simple. Distance has always felt like a wall. We push harder to go faster and reduce the wall. For deep space, another path is to make time less sharp for the traveler. A safe sleep turns long silence into a brief pause for the person on board. A better engine turns years into months. A more efficient sail turns steady light into motion without fuel. None of these ideas need to be perfect to matter. Even partial torpor changes logistics. Even moderate fusion performance reshapes routes. Even modest laser arrays open new mission classes for tiny probes that scout ahead. The measure of progress will be practical. Can we cool a person a few degrees safely for weeks? Can we revive without harm and repeat the cycle? Can we ignite fusion in compact systems and direct the exhaust? Can we hold antimatter long enough to use it for more than seconds? Can we build sails the size of fields that fold and deploy without tearing? Each question has a test. Each test moves the line between plan and reality. Meanwhile, light keeps setting the pace card. The moon remains a second away by light. The sun is minutes. The giants are tens of minutes to hours. The nearest star is years. Those numbers will not change. What can change is our relationship to them. A crew that sleeps through a cruise will feel the trip as a set of wake windows, not as a continuous wait. A ship that can accelerate harder will put more of the trip into approach and science and less into coasting. A small probe pushed by lasers will cross the inner system in days and send back fast snapshots that guide larger missions that follow. The direction is clear. Shorten the time people must spend awake between worlds. Raise the energy we can safely direct into motion. Keep systems simple, robust, and quiet, because quiet machines last. Accept that light time delays are part of deep space and design crews and craft to thrive with that delay. Together, these steps reshape the outer system from a once-per-generation reach into a set of destinations on a steady schedule. The ice giants, the Kuiper Belt, and the thin edge of the heliosphere become places for repeated visits, not rare flybys. The path there is not a single leap, but a set of modest gains: cooler sleep, hotter engines, lighter sails, smarter autonomy. Each gain bends the timeline toward the human scale, without breaking the rules that hold the universe together. When a ship moves at extreme speed, time changes for the people aboard. To those on Earth, the traveler's clock runs slow. This effect, called time dilation, comes from relativity. It does not feel strange to the traveler. Heartbeats, thoughts, and work all seem normal. The difference shows up only when clocks are compared across distance. A trip that takes decades by Earth's calendar could feel like a handful of years on the ship. Near light speed, the gap widens. What once seemed unreachable becomes a route measured in a small slice of a life for the crew, while many years pass at home. Small versions of this effect have already been measured. Astronauts in low orbit age a tiny amount less than people on the ground because of their speed and the weaker gravity at altitude. The gap is measured in microseconds, but the physics is the same. Increase the speed and the gap grows. At 9/10 the speed of light, time on the ship runs more than twice as slow as on Earth. At 99%, it slows by about a factor of 7, push even closer to light speed, and a single year on board could line up with centuries passing at home. Distance shrinks for the traveler. Time becomes the price. A 5-year voyage by the ship's clock might return its crew to a world 50 years older. Friends would be elders. Cultures would have changed. History would have moved on without them. Relativity also limits how we approach such speeds. Energy demands rise steeply as velocity climbs. Getting close to light speed takes more than better engines. It takes ways to handle heat, shielding, and control at power levels beyond anything in use now. The universe does not ban speed outright. It sets a rule. Nothing with mass reaches light speed. Within that rule, trade-offs remain. Crews can shorten their own felt time by flying faster, but the price is energy, risk, and a growing gap with home time. With that in mind, distance and time blur into a single measure of travel. We speak about miles and orbits, yet what shapes a mission is often the calendar. A round trip to the far edge of the solar system could be 30 years for Earth and much less for a ship running near light speed. The ship's log would be short and intense. The ground logs would span generations. Myths about leaving home and returning to a place, changed beyond recognition, turn out to describe a real outcome of fast travel. The faster we move through space, the slower our own time runs. The cost of seeing more of the universe is stepping further into its future. The same pattern appears when we read the solar system itself as a record of time. Each world holds a chapter. Mercury keeps scars from the first hot days of formation. Venus shows the result of a greenhouse effect that ran away. Earth carries weather, water, and life. Mars holds traces of rivers and lakes, now gone. The giant planets store heat and carve paths with gravity. The small icy bodies in the deep outer region keep ancient ices and dust. Moving outward is not only crossing space, it is moving through different eras written into rock, ice, and air. From far away, the inner planets turn into points of light. Earth is a bright dot no bigger than a star in the camera. In that dot is all of human history. Borders and divisions vanish at that scale. What remains is the fact of a living world and our awareness of it. That awareness matters. It is the reason the record can be read and shared. We measure storms that last for years on Jupiter. We watch nitrogen creep across bright plains on Pluto. We track the fading breath of the sun as its wind thins near the edge of the heliosphere. Time in the system is not one river. It is many slow loops and cycles, interlocked and moving at different speeds. Near the limit of the sun's reach is the heliopause, where the solar wind yields to the thin gas between stars. Beyond that lies true interstellar space. Farther still sits the Oort cloud, a deep, cold shell of small bodies. It likely holds trillions of icy fragments left from the birth of the planets. This region is vast. It could take a spacecraft tens of thousands of years to reach its outer edge. Comets we see from Earth may begin their journey there, nudged inward by passing stars. They carry old material into the warm light, then return to the dark for another immense arc. At that scale, even the nearest star system is far. Alpha Centauri is a little over 4 light-years away. At current probe speeds, the trip would be on the order of tens of thousands of years. A radio message would take 8 years for a round trip. In the space between stars, there are no bright suns to guide a quick path, only thin gas, dust, and the occasional rogue planet or brown dwarf. Yet the map is not empty. It is studded with targets that hold heat, chemistry, and mystery. The logic of the solar system: use gravity well, save energy, protect your craft extends outward with new tools and longer plans. The question, how long to reach another star, turns into several linked questions. How long to keep a ship healthy? How to carry or grow what people need? How to keep minds and cultures strong over long spans? Ships that host multiple generations are one answer. Deep sleep that reduces a traveler's felt time is another. High-energy drives shorten the calendar for everyone. None of these erase the rule of light time for signals. A fast ship is still far when it comes to torque and control. That pushes autonomy aboard and patience at home. Standing at the far edge of the sun's wind, the pattern is clear. Planets are not only places, they are snapshots in time. Jupiter shows weather on a scale we do not have on Earth. Saturn's rings record impacts and moon interactions in ripples and gaps. Uranus and Neptune slow seasons and show long, quiet shifts in deep cold. The Kuiper Belt and its dwarf worlds keep early chemistry in place. The Oort cloud holds the oldest, coldest store of the system's raw materials. Reading them all at once changes how we think about travel. We are not just moving outward on a straight line. We are moving through a landscape of clocks. That view does not make Earth small. It makes it rare. It is the place where rocks, air, water, and life all work together. The fact that we can map other worlds and ask how long it takes to reach them shows that awareness itself is part of the system's story. We are matter and energy, arranged in a way that can look back and measure. The same iron that sits in a meteor sits in our blood. The same water ice that drifts in a comet runs in our rivers. The connection is physical and also practical. The tools that let us read the solar system, cameras, spectrometers, radios, are simple in principle, just carefully built and patiently used. Ahead lies the wide region of interstellar space. Getting there in a way that fits human life means making time a partner. There are 3 main levers. One is speed, better drives to push faster and coast less. Another is biology, safe torpor to let people skip the long, empty spans. The third is culture and design, ships that can last, crews that can thrive, and plans that accept delay instead of fighting it. Each lever changes the same measure, the calendar of a mission. Pull any two, and the solar system shrinks to human terms. Relativity sits under all of this as the rulebook. It tells us why light takes minutes to cross the inner system and hours to cross the outer. It tells us why fast ships can compress their own time while letting home time run ahead. It explains why reaching light speed is not on the menu, and why space itself, not just objects in it, shapes what a path means at high energy. It also gives hope in a quieter way. It shows that speed and time are not fixed experiences. They depend on the frame of the traveler. That means there are many workable plans, not just one. We can go a bit faster and sleep a bit longer. We can accept a slower ship if the people aboard live most of the cruise in safe rest. We can send small scouts first and follow with heavier craft later. Each plan thinks in time as much as in distance. As the view widens, the solar system stops looking like a set of isolated targets and starts looking like a connected field. Gravity links bodies across space. Light links them across time. Storms, rings, oceans under ice, thin airs that come and go, planes that creep and change each feature is a marker on a timeline. Our tools convert those features into dates and processes. They turn wonder into knowledge without losing the quiet feeling that drives us to look in the first place. If the outer edge is a threshold, it is also a lens. It shows us that the next step is not only technical, it is also about how we think of travel over long spans. Can a crew accept waking into a future they did not live through and call the mission a success? Can a society plan for missions that deliver their best results after the planners are gone? Can we write guides and build systems that stay clear and kind across a century? These are not physics problems. They are design and duty problems. They borrow the same patience we already use to land a robot after years of flight or to wait for a comet to return. Numbers keep the story concrete. Light moves about 186,000 miles each second. The sun's light reaches Earth in just over 8 minutes. A signal to Jupiter can take half an hour. To Neptune, hours. A year on Uranus is 84 Earth years. A year on Neptune is 165. Pluto takes 248. The Oort cloud may reach tens of thousands of times the Earth-Sun distance. Alpha Centauri is a little over 4 light-years away. These values are more than trivia. They tell us why the inner system feels close, why the outer feels slow, and why the step to the stars is large but not blank. In that frame, the end of the sun's wind is not a finish line. It is a marker that says the next medium has begun. The gas and dust between stars carry their own fields and waves. They shape how a ship charges, how radios behave, and how dust strikes at speed. Crossing that medium is not a trick. It is a job of steady planning. The skills we practice in the solar system, careful burns, patient data returns, long hardware life map directly onto that job. The arc of the trip through our system started with a simple question about time to each planet. It became a map of how time itself plays through rocks, winds, rings, and ice, and through our own bodies and clocks. The farther we went, the more it became clear that the measure that matters is how deeply we understand where and when we are. Distance matters for fuel and flight. Time matters for meaning. When those two are handled well together, the path forward stays open.